Good morning. Okay, today we're going to go over section 6.7, hyperbolic trig functions. And so let's just get started, okay? All right, so we're going to define some new functions that you have probably never seen before, but actually have a lot of value, a lot of use to them. So let's just get started with it, and then we'll try to explain, first of all, why are they called hyperbolic functions, or hyperbolic trig functions is what I call them. All right, so here's the funny one. The first one, I have some funny names. Okay, so we write this sin h of x. Okay, and you read this as sinh of x. At least that's how I read them. Okay, sinh of x, which is hyperbolic sine. So we'll write that as hyperbolic sine. And the way we define hyperbolic sine is like this: e to the x minus e to the negative x over 2. Okay, e to the x minus e to the negative x over 2. Now, just like we have hyperbolic sine, we're going to have hyperbolic cosine and hyperbolic tangent. All right, so hyperbolic cosine is very similar to sine. It's e to the x plus e to the negative x over 2. And then hyperbolic tangent, believe it or not, is actually just hyperbolic sine over hyperbolic cosine. The quotient identity from trigonometry shows up here with hyperbolic trig as well. Okay, now for hyperbolic cosine, we usually say cosh. So we can say cosh of x. And for hyperbolic tangent, we say tanh, which sounds really weird, I know, but we have sinh, cosh, and tanh. Okay, now what about the normally what we call the reciprocal functions? Yes, we have those. So you have cosech is 1 over sinh. You have sech is 1 over cosh. And then you have, it looks like coth, but I guess you can say cotanh or coth, however you want to say it. And we just define that. Notice we are defining these by the trig identities that we're used to seeing, right? And so this is kind of a weird deal, isn't it? I mean, we have these e to the x expressions, and we're trying to relate that to trigonometry somehow. And I'm going to show that it really does relate to trigonometry, just maybe not in a way that you normally think of, or maybe in a way you wouldn't expect necessarily. Okay, and let me give you a quick look at some of the graphs here. I'll give you the graph of sinh and cosh, and as far as physical applications, cosh is usually what shows up the most. But anyway, let me show you. Okay, so I'm going to graph sinh first, and there's a couple of graphs I want to draw in here. So one is y equals 1/2 e to the x power. Okay, that's 1/2 e to the x power. The other one goes like this. This is 1/2 e to the negative x power. Okay, sorry, times -1, right? Because it pushes it below the x-axis. So we have these two graphs here. And what happens is, as x approaches infinity, or negative infinity of sinh, we approach these two curves. And so your actual curve looks like this. So these, we pass right through the origin, and then see as x approaches infinity, this thing approaches 1/2 e to the x. As x goes to negative infinity, this thing approaches -1/2 e to the negative x. They're kind of like asymptotes. We call them curvilinear asymptotes. All right, so they're not exactly asymptotes because they're not straight lines, but they operate like the way an asymptote works. And so this is the graph of sinh, the purple line, okay? Now we can do the same thing with tangent. And so this time we need 1/2 e to the x, and we need positive 1/2 e to the negative x as our two boundaries. And so it looks something like this. 1/2 e to the x, and then negative, or not negative, positive 1/2 e to the negative x. I keep wanting to write that as a negative. 1/2 e to the negative x power. And those are my two curvilinear asymptotes for cosh. Your graph looks something like this. So as x approaches negative infinity, this thing's going to approach 1/2 e to the negative x. As I go to positive infinity, it's going to approach 1/2 e to the positive x. Okay, now an interesting thing here. I guess let's do our third one. I say an interesting thing. They're all interesting, right? So if I look at tanh, I have horizontal asymptotes at 1 and -1, and my graph looks something like this, which looks very similar to tan inverse, really. Okay, except that would have asymptotes at pi over 2, negative pi over 2, but that is my graph y equals hyperbolic tangent, or tanh. Okay, so these are the three graphs we're going to look at. Now, the one that we see in physical applications a lot, again, is this cosh. And where you see that is if you had a flagpole, I mean not a flagpole, you have two telephone poles with a dangling cable in between them. Okay, so, and that's kind of what this looks like, doesn't it? I mean, so here's where you normally see this. Let's see, let's get some grass. And then we have some sort of pole, or we can do like an antenna. Okay, something like that. And then we have this cable, kind of, that's not a very good picture. Let me try again. You have a cable kind of dangling, and it goes up like this. We call this a catenary, that structure, that dangling cable structure, and it is modeled by cosine, not cosine, cosh, hyperbolic cosine. And the exact equation looks like this. You have some sort of vertical translation based on your height, and you have some sort of scaling factor, cosh, x over a, and that scaling factor depends on what kind of cable you have. But this is how we model a catenary, right? So we can figure out like how long I have these two poles together and I have this amount of rope, or why would you hang rope? Maybe cable, and we need to know, is it going to clear the bridge or not? Is it dangling too low? We can use this function to help us figure that out. Okay, now another situation where you see this, and this is in the book, but if you are looking at the way ocean waves travel and you're looking at the velocity of these ocean waves moving, you can actually measure that with hyperbolic tangent. Now, the mathematics behind the way water flows is very, very complicated. And in fact, if you can solve some fourth order differential equations involving the movement of water, you're going to get $1 million prize. That's one of the Millennium Prizes, looking at fluid dynamics. But in this particular instance, we can model a solution through hyperbolic tangent. And it turns out in differential equations, the hyperbolic trig functions show up from time to time. And so they do model real life situations. Okay? And again, they're coming back to, where are we getting these again? Just keep this in mind. The definition of sinh and cosh, e to the x minus e to the negative x over 2, e to the x plus e to the negative x over 2. Now the funny thing is, with these hyperbolic trig functions, is that a lot of our common identities from trigonometry carry over in some way or the other. It's either the same or just the same with a little variance, and I'm going to show you some of those. Alright, so let's look at some hyperbolic identities. and we'll try to compare them to their just pure trigonometric counterpart. So one is that if you had a negative x and plugged it into sinh, you can factor out that negative. And that's exactly how sine works as well. We call this odd. Sinh and sine are both odd functions. On the other side, cosh and cosine are both even. So if I plug in negative x, I just get the same thing as cosh x. And I guess if we just have cosh x, we don't need the parentheses there. Okay, so that's how sine and cosine, or sinh and cosh, are odd and even respectively. Now, we don't get the Pythagorean identity, but we get something very similar. Cosh squared minus sinh squared equals 1. So in trigonometry, so we cosine theta plus cosine squared theta plus sine squared theta always equals 1. In hyperbolic world, it's subtraction. Cosh squared minus sinh squared equals 1. And you could come up with a similar, we shouldn't say the Pythagorean identities, but we have something similar to that. 1 minus tanh squared equals sech squared. Okay, and we remember that's the same as the trigonometry version of this, except instead of minus it's plus. 1 plus tangent squared equals secant squared. Okay, you also have your sum and difference identities that are very similar. We'll just do sinh of x plus y. So in sine of a plus b, for example, is very similar to this. It's sinh x cosh y plus sinh y cosh x. Now, the only way that's different from normal trig is the normal trig sine of x plus y is sine x cosine y minus sine y cosine x. Okay, and cosh, so cosh of x plus y is cosh x cosh y plus sinh x sinh y. So we basically get the same thing. Okay, so I'm hoping this makes sense. This trig is a little bit different. It's not defined from a triangle, right? It's defined from e to the x power, but we end up getting a lot of the same or similar identities, and we'll see other things looking similar as well. All right, now just as an exercise, this is an example from the book. This first identity, or actually the one I labeled number 3, is pretty easy to prove. Let's do that. So let's prove that cosh squared minus sinh squared does in fact equal 1. And how on earth can we prove this? We don't know a lot about sinh and cosh. Well, I guess we do now. We've looked at their graphs. We've seen some identities. We haven't really worked with them a lot. But let's go back to the definitions again. Sinh is e to the x minus e to the negative x over 2. Cosh is e to the x plus e to the negative x over 2. Let's use those facts to plug this in and see if we really do get 1. Okay, so I'm going to say cosh squared minus sinh squared equals, by definition, e to the x. Now is cosh plus or minus? Let's go back and review one more time. Cosh is plus, sinh is minus. If you want to remember this way, sinh is subtraction, right? The s carries over in alliteration. So we have e to the x plus e to the negative x over 2 quantity squared minus e to the x minus e to the negative x over 2 quantity squared. All right. Now, how do we FOIL these out? So in the denominator, we just have 2 times 2. We're going to end up with 4 in both cases. In the numerator, we're going to have to do some FOILing. And let's come over on the side and see if we can figure that out. So we have e to the x plus e to the negative x times e to the x plus e to the negative x. Okay, so when I multiply this out, you have to add the exponents, right? So x plus x gives me 2x when I multiply e to the x times e to the x. On the inside, I have e to the x plus e to the x times e to the negative x. Adding the exponents, you end up with e to the 0. Inside terms, same deal. You end up with e to the 0. And then last, e to the negative x times itself. You add the exponents, you get negative 2x. And e to the 0 is 1, so I end up here in the numerator with e to the 2x plus 2 e to the negative 2x. Does that make sense? I hope so. Okay, now that's the first one. The second one, what do we get? We have a 4 in the denominator again. And now I'm going to multiply this out again. So let's do the same calculation. Let's just change our plus in the middle here to minus. See what happens. So you end up with e to the x times e to the x, so that stays the same. You have e to the x minus e to the negative x, so I get a negative 1 there. On the inside, I end up with a negative again. And then lastly, I end up with negative e to the negative x times negative e to the negative x becomes positive e to the negative 2x. So I get a very similar thing here. I end up with e to the 2x minus 2 plus e to the negative 2x. And I am subtracting all of that. So when I subtract, I have, well, let's think, e to the 2x minus e to the 2x, that goes away. E to the negative 2x minus e to the negative 2x, that goes away. And end up with 2 minus a negative 2, which ends up becoming 4 over 4. Lo and behold, we get 1, which is exactly what we were hoping to get. Isn't that amazing how that works? Okay, so the definition here makes sense then that we would get this relationship between cosh and sinh. Okay, good. All right, now before we look at the derivatives, let me explain why they call this hyperbolic trig, okay, or hyperbolic functions. So in trigonometry, one way we think about trig is, let's start off with a circle. We have a unit circle here. And the unit circle here has a radius of 1. That's why it's called the unit circle, right? And if you do that, because you can drop a triangle down here at any point with a radius 1, and cosine is defined as adjacent over opposite, and sine is defined as opposite. Cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. We end up with any point along here has the points or the coordinates cosine theta, sine theta, where theta is the angle of our rotation there. Okay, that's what we did in trigonometry. And so because of that, and remember the equation of a circle is x squared plus y squared equals r squared, which in this case is 1. And we just said that the x coordinates are my cosines and the y coordinates are my sines. I end up with the Pythagorean identity that we know and love, that we use a lot. Okay, now in hyperbolic world, we can't look at x squared plus y squared equals 1. We look at x squared minus y squared equals 1, which translates to, hopefully, cosh squared x, or we should say theta, minus sinh squared theta equals 1. Okay, and what kind of geometric figure has this equation, x squared minus y squared equals 1? If you've forgotten that, hopefully the adjectives that we've been using this whole time is a little bit of a tell. That's right, we're looking at hyperbola, a hyperbola instead. So x squared minus y squared equals 1 has this graph. Okay, we have the hyperbola here. And in a way, this is kind of like our unit hyperbola. And what happens here is we rotate an angle. So that's our theta angle rotated over. And the point on the hyperbola with the angle theta is cosh and sinh. I hope that makes sense. Okay, and you can see here, if we let, for example, y be 0, we get x. If y is 0, we get x to be positive or negative 1. So that's kind of why you can think of this as like the unit hyperbola, is that we have our x-intercepts at 1 and negative 1. And other than that, we will follow this equation. And that's how we get hyperbolic trig functions. That's why we call it hyperbolic functions. And which is pretty neat. And you probably have never thought about this, but it's kind of, I like teaching this section because it's kind of fun to all of a sudden see there is a new side of trigonometry that we've never seen before, and it operates exactly how we would hope it would. All right, well, up to this point. Let's see now, what about like derivatives and things like that? Okay, so derivatives of hyperbolic functions. All right, so one, if I take the derivative of sinh x, don't you hope that we get cosh x? And we actually do. Okay, and I'm not going to prove all of these, but let's think about that one. Why would that work? Because remember, I'm taking the derivative of e to the x minus e to the negative x over 2. And when I take the derivative of e to the x, what do I get? I get e to the x. Good. When I take the derivative of e to the negative x, I get negative e to the negative x, right? Because it's e to the negative x times the derivative of its exponent. The derivative of its exponent is negative 1 over 2. And so that minus in the middle becomes a plus, and I end up with cosh x. That's exactly how it works. It's pretty incredible. Okay, let's continue then. 2. The derivative of cosh. Well, the derivative of cosine is negative sine. In hyperbolic world, it's just sinh. It's not negative sinh, it's just sinh. Okay, for a tangent, and how could you verify that? Just like we did with the first one, taking the derivative of e to the x plus e to the negative x over 2 and just seeing what you get. The derivative of tanh is sec squared x, just like we had with normal trig functions. And then the others follow a similar pattern from what we're used to, just with negatives. So I'll go ahead and write them out. The derivative of cosec is going to be negative cosec x cotanh x, right? Which is consistent with the derivative of cosecant. Okay, the derivative of sec is consistent with the derivative of secant, except it's negative. Instead of saying secant tangent, we have negative sec x tanh x. And then lastly, the derivative of cotangent x is negative cosec squared x. Okay, so there are my derivatives of hyperbolic functions. And if we know our derivatives of tangent functions, these should be pretty straightforward, right? Okay, now let me give you an example. This is example 2 in the book. Let's find dy dx, where here this time y equals cosh square root of x. Okay, so this is just a matter of applying chain rule. All right, so I'm going to take the derivative. And how do you do chain rule? Well, notice the outside is the cosh, inside is the square root. So here, when I take the derivative, first you do the derivative of the outside. So the derivative of cosh is sinh. Leave everything in the middle alone. And now you take the derivative of what's inside, which would be the derivative of this is the same thing as x to the 1/2 power, right? So it's going to be 1/2 x to the negative 1/2. 1/2, then you subtract 1 from the power to get negative 1/2. And so if you want to write this a little cleaner maybe, you get sinh square root of x over 2 square root of x. And there's your derivative. We just applied chain rule and then a little bit of algebra to simplify. Hope that makes sense to you. Okay, now we just finished talking about inverse trig functions, and now we have hyperbolic functions. So does it make sense to talk about inverse hyperbolic functions? And it does. And really, inverse hyperbolic functions they find their use in integration, which we'll see in a second. Okay, so I'm going to, I think we understand what we mean. So if I say, what does this mean? I think we understand from our discussion with inverse functions and our discussions from inverse trig that we understand that means that sinh y equals x. Okay. Now, the funny thing is, don't you remember that sinh is defined using exponentials? So what happens here is that if I'm doing the inverse function of this, so let me do example 3 and I'll kind of lead to where I'm going. We're going to end up with logarithms because the inverse of exponentials is logarithms. Okay, so this is example 3. And then after this, we'll write our logarithm definitions of inverse hyperbolic tangent and hyperbolic cosine and sine. Okay, so we're going to show that sinh inverse of x is the same thing as saying ln of x plus the square root of x squared plus 1. Okay. All right, so how do we do this? Let's let y be this sinh inverse x. Okay, then that means that x is the same thing as sinh y by definition of the inverse function. And now I can apply my definition of what sinh y means. That means e to the y minus e to the negative y over 2. And now we need to solve this in terms of x, okay? Or I'm sorry, in terms of y. We need to solve for y here to figure out what sinh inverse x is. Anyway, okay, I'm losing myself in my terminology. Okay, so solving this, look, if I multiply both sides by 2, I get 2x equals e to the y minus e to the negative y, which means then I can say e to the negative y minus e to the y plus 2x equals 0, right? And now what I can do, and actually let me rearrange these terms. Let's rearrange this to say, and let's multiply both sides by -1. I'm going to end up with e to the y minus 2x minus e to the negative y equals a -0, which is just 0. And I'm going to multiply both sides of this equation by e to the y. Okay, now I'll show you why I'm doing that. Because now I have e to the y quantity squared minus e to the y 2x minus, what is that, 1 equals 0. Okay? And now I can solve this by using the quadratic formula. Because look, here I have something squared times something to the first power minus 1. For example, if you let a be e to the y, then I end up with a squared minus 2x times a minus 1. And now I use the quadratic formula to solve for a. And so I get e to the y equals, according to the quadratic formula, negative b plus or minus 2a. Okay, negative b, which is going to be 2x, plus or minus the square root of b squared, which is 4x squared, minus 4ac, which in this case is going to be 4 times 1 times 1. So I end up with 4 times negative 1 times 1, so I end up with plus 4 all over 2 times a, which is 2. All right, and so notice that that's going to reduce to, look, I can take out I have 4 in the square root factored out. I can take out a 2 and then cancel out the 2's. I end up with x plus or minus the square root of x squared plus 1. Now, thinking back to what I started with, when I thought, how on earth am I going to get all that? Here it is. I have e to the y equals that. So that means then, taking the ln of both sides, y equals ln x plus square root of x squared plus 1. What happened to the x minus x squared plus 1? So remember, I'll put a little note here. Recall, e to the y is always positive, and so we don't need to consider the x minus the square root of x squared plus 1, which is always negative. Okay, so e to the y can't possibly be a negative value, so that's how we only end up with the positive one. And there we have it. Okay, let's do an end of proof there, because that's basically a proof. And that may have been a little bit longer than we expected. Okay, we could do the same thing with cosh and tanh, and when we do, we end up with these rules. Okay, so let's say rules. 1, sinh x inverse, sorry, let me write that again. Since inverse of x is what we just said, ln of x plus the square root of x squared plus 1. Okay, and then I think now hopefully it makes sense that we can get that through our derivation. Now cosh inverse of x in a similar way is going to be ln of x times the square root of x minus 1. Okay, and then tanh inverse, just by the definition of what tanh is, gives us 1/2 ln 1 plus x over 1 minus x. All right, and here we need to specify a few things. First of all, for sinh inverse, this works for any real number, but for cosh inverse, we have to make sure that x is greater than 1. Otherwise, our square root's going to be negative, and we can't have that. And for tanh inverse, we need to make sure that we're between negative 1 and 1 for the same reason. We can't have a negative logarithm. Negative logarithms don't exist. So these are our definitions. Another way of formulating our inverse hyperbolic functions. So sometimes if you see a table of integrals and you're looking for an integral, sometimes it might have a hyperbolic inverse expression. Sometimes it might have a logarithmic inverse expression or a logarithmic expression. And sometimes we don't understand how those two are connected. Well, here's how they're connected through these rules. Okay, good. All right, now, so since I have these logarithmic definitions of the inverse trig hyperbolic functions, it would make sense then to consider the derivatives of these functions. And I'm glad you asked. So let's look. Derivatives of inverse hyperbolic functions. And how are we getting these? Through these expressions. So instead of saying the derivative of sinh inverse, which is what I'm considering, the derivative of sinh inverse, how do I calculate that? By taking the derivative of ln x plus the square root of x squared plus 1. And when you do that, you end up with, we won't go through the details, but you end up with 1 over the square root of 1 plus x squared. Now, you can see how this would be useful because I'm thinking ahead of the game. I'm thinking of integrals. And to this point, we don't know how to integrate 1 over the square root of 1 plus x squared. But now we do. the integral of that is going to be sinh inverse. Okay, or this logarithm, ln of x plus square root of x squared plus 1. Okay, cosh inverse, it's a similar game, right? We're going to end up with 1 over the square root of x squared minus 1. And the derivative of tanh inverse x is going to be 1 over 1 minus x squared. Okay, now if you remember the derivative of arctan, or tan inverse, is what I wrote, 1 over 1 plus x squared. The derivative of tanh inverse is 1 minus x squared. All right, now those are the only three I'm going to write down. Okay, if you're having to use integrals involving, or derivatives involving cosec inverse, etc., at that point we can probably just reference it. We can look it up. I usually don't make people memorize those. I think those are things that we can easily reference. Okay. All right, so let's try an example with one of these. And I'm out of room, so let me come up at the top again. All right, and let's look at example 5 from the text. And I want to take the derivative of tanh inverse sine x. So I'm putting sine x into the tanh inverse function. Okay, so we're having to use chain rule here. Recognize, please, that the outside is the inverse tanh, the inside is the sine. So when I take the derivative, my dy dx is, okay, we're going to use the derivative of tanh inverse, which we just said is 1 over 1 minus what's inside squared. So it's going to be sine squared times the derivative of what's inside. The derivative of sine is cosine x. Okay. Now, so this is going to be interesting. All right. So we have, again, 1 over 1 minus u squared, u here being sine, so I have sine squared, times the derivative of what's inside, which is cosine x. Now remember here, Pythagorean identity, cosine squared plus sine squared equals 1, which means that 1 minus sine squared x equals cosine squared x. So this denominator is actually 1 minus sine squared is actually the same thing as cosine squared times cosine x. One of those cancels out, so I end up with 1 over cosine x. The derivative of hyperbolic tangent of sine x simply is secant x. Did not see that coming. Did you see that coming? Probably not. It's amazing how this stuff kind of telescopes in on itself, right? Okay, now where these things again show up to be useful is through integration. And let me do an example of that. So here I want to integrate, and I don't need to make a new table because we understand the fundamental theorem of calculus. If I see the derivative, then I know how to find the antiderivative of that derivative, right? So what I mean here, let's go back down to my table. If I see an integral involving 1 over the square root of 1 plus x squared, I know then I'm looking at an inverse hyperbolic trig function. Okay, so let's go back at the top, and what we want to integrate now is from 0 to 1 dx 1 square root of 1 plus x squared. All right, and this is just what we figured out here. So that's going to be, just using our table, that's going to be sinh inverse of x, going from 0 to 1. Okay, so can I figure out then what sinh inverse of 1 minus sinh inverse of 0 is? May I suggest using our logarithmic definitions, and again, hyperbolic, or sinh inverse of x is ln of x plus the square root of x squared plus 1. So I end up with ln plus the square root of 1 squared plus 1 minus ln of 0 plus square root of 0 squared plus 1. Alright, so the second ln, let's just think, that ends up being ln 1. Ln 1 is simply 0. Okay, so here I end up with just ln of 1 plus root 2 minus 0. So there's my answer. Ln of 1 plus root 2. And there it is. I hope that makes sense. Okay, let me do one more real quick. And we'll do, this will be an indefinite integral, so I don't have to plug in anything. Oops, where'd I go? Okay, and just give me a second, let me think about what I want to do. How about square root of 1 plus x to the fourth and we have x in the numerator dx. Okay, so if you're trying to integrate this, first thing you would try to do is maybe u substitution. So u is x to the fourth, that's not going to work. So if u is x to the fourth, du then is 4x cubed dx. There's no way I can get an x cubed dx. This is not going to work. So we got to try something else. You might be tempted to try u is the square root of 1 plus x to the fourth. Well, that's going to even be worse, because then you have to have a square root in the denominator times 4x cubed dx. We're not going to get very far with that either. That's not going to work. Alright, so what we should try then, and really the only thing we can do, is let's let u be x squared. Now if I do that, the du is 2x dx, meaning that I have 1/2 du is x dx. I do have that. I can say then that this is the same as 1/2 the integral of x dx is my du, square root of 1 plus u squared. Alright, so now I get 1/2. What's this integral? Well, that's just what we just did. Dx over square root of 1 plus x squared. This is hyperbolic inverse of u. So then finally, I end up with 1/2 sinh inverse of x squared. Okay, now depending on what book you have, that if you look this up in a table of integrals, that might be what you see. Oh yeah, don't forget the plus c. Or if, depending on your book again, you might have the logarithmic definition, which would be 1/2 ln u plus the square root of u squared plus 1. So you might see it written as a logarithm, or you might see it written as sinh inverse. Okay, it just depends on your book. Guys, I hope this makes sense. Hyperbolic functions are fascinating. They show up kind of in unexpected ways. Don't forget that behind them, what's really going on, it's e to the x, right? And so you have to know the definitions. The funny thing is that a lot of the trig carries over in derivatives, integrals, even our identities, but we're looking at a hyperbola instead of a circle. All right, I hope this makes sense, guys. If you have any questions, let me know. I'd be glad to help. And I guess we'll see you later. Have a great day.